It came through at 22.4 hours after the last scheduled transmission window. Not a malfunction alert, not a systems error, a signal. Clean, structured, and unlike anything Voyager 2 had sent back in its entire 47-year journey through space. The engineers at the Deep Space Network who first received it did not immediately tell anyone outside the room. They ran the decoding sequence 3 times. They checked the timestamp against the orbital position data. They verified the signal origin against the known trajectory of the spacecraft. Everything confirmed the same thing. The signal was real. It came from Voyager 2, and the data embedded inside it described an environment that nothing in our current models of the outer solar system had predicted would be there. By the time the analysis team had assembled and the senior mission controllers had been notified, 6 hours had passed. The data was being processed in fragments across 3 separate institutional servers, and somewhere in those fragments, buried in the telemetry of a 47-year-old spacecraft running on a nuclear battery producing less power than a refrigerator light bulb, was a measurement that changed everything we thought we knew about what exists beyond the edge of the solar system and what might be waiting in the darkness on the other side of everything we can see. Voyager 2 launched on August 20th, 1977, 47 years ago, when the most powerful computer on Earth had less processing power than the phone sitting in your pocket right now. NASA engineers calculated a trajectory so precisely that it used the gravitational fields of Jupiter, Saturn, Uranus, and Neptune in sequence to accelerate a small spacecraft to a velocity that would eventually carry it out of the solar system entirely. The planetary alignment that made this grand tour trajectory possible occurs only once every 176 years. They had one window. They hit it perfectly. Voyager 2 flew past Jupiter in 1979, Saturn in 1981, Uranus in 1986, and Neptune in 1989, becoming the only spacecraft in history to have visited all 4 of the solar system's outer giants and returning images and data that rewrote planetary science at every encounter. And then it kept going, past the Kuiper Belt, past the scattered disk, past the heliopause, the boundary where the solar wind, the constant stream of charged particles flowing outward from the sun, finally loses the battle against the pressure of interstellar space and is pushed back. In December 2018, mission controllers confirmed that Voyager 2 had crossed the heliopause and entered interstellar space, becoming only the second human-made object in history to leave the solar system, following Voyager 1, which had crossed the same boundary 6 years earlier. Beyond the heliopause is a region scientists call the very local interstellar medium, the space between the stars, the true darkness beyond the solar system's protective bubble. And it is from this region, from a distance of more than 12 billion miles from Earth, that the anomalous transmission came. To understand why what Voyager 2 detected is so significant, you need to understand what the heliopause actually is and what it was expected to protect us from. The solar system exists inside a vast bubble of charged particles and magnetic field created by the sun's constant output of solar wind. This bubble, called the heliosphere, extends outward from the sun in every direction, pushing back against the interstellar medium, the thin sea of gas, dust, magnetic fields, and cosmic rays that fills the space between stellar systems. The boundary where the solar wind's pressure finally equals the pressure of the interstellar medium is the heliopause. Inside the heliopause, the environment is shaped and dominated by our sun. Outside it, the environment is shaped by forces entirely independent of our solar system, forces whose origin lies in distant supernovae, stellar nurseries, galactic magnetic field structures, and processes operating on scales of thousands of light years. Before Voyager 1 and Voyager 2 crossed the heliopause, everything we knew about the interstellar medium beyond it came from remote sensing observations and theoretical models. We had never put an instrument directly into that environment and measured it in situ. What both Voyagers found when they crossed the boundary was broadly consistent with predictions, but contained several measurements that did not match the models precisely. The magnetic field direction outside the heliopause was different from what the models predicted. The density of the interstellar plasma was higher than expected, and the cosmic ray environment, the flux of high-energy particles streaming through the interstellar medium from distant sources, was more intense and more structured than the smooth, uniform distribution the models had assumed. But all of these discrepancies, while scientifically interesting, fell within the range of things that could be explained by adjusting the models. What Voyager 2's final transmission describes falls into an entirely different category. The transmission contains plasma wave data. Voyager 2 carries a plasma wave subsystem, an instrument designed to measure the density and motion of charged particles in the surrounding environment by detecting the electromagnetic waves those particles generate. In the heliosphere, this instrument measured the properties of the solar wind plasma. After crossing the heliopause, it began measuring the properties of the interstellar plasma. For the years since crossing the boundary, the readings had been consistent, showing the expected properties of the local interstellar medium at Voyager 2's distance and position, and then the readings changed. Not gradually, not in a slow drift that might indicate the spacecraft was moving into a slightly different region of interstellar space. Abruptly, the plasma density reading shifted by a factor that the instrument team initially assumed was a calibration error. When they ruled out calibration error, the next explanation was the one nobody in the room wanted to say out loud. The environment outside Voyager 2 had changed. Something in the interstellar medium at Voyager 2's location was different from what had been there before, and the pattern of that change, the specific way the plasma density and the associated magnetic field readings shifted together, matched the theoretical signature of something that astrophysicists had proposed might exist at the outer boundary of our local interstellar neighborhood, but had never directly detected: a density enhancement at the edge of the local interstellar cloud. The local interstellar cloud is the name given to the specific region of interstellar space that our solar system is currently traveling through. It is an enormous cloud of warm, partially ionized gas, approximately 30 light-years across, through which the sun and its entire retinue of planets and moons and comets and spacecraft have been moving for somewhere between 45,000 and 150,000 years. The solar system entered the local interstellar cloud from one direction and is moving towards its edge at the opposite boundary. Models of the cloud's structure had predicted that its edge would not be a sharp, clean boundary, but a gradual transition region, a zone where the density and temperature and magnetic field of the cloud material grade slowly into the properties of the surrounding interstellar medium. But the plasma wave data from Voyager 2's final transmission does not show a gradual transition. It shows an abrupt one, a boundary that is far sharper and far more structured than the models predicted. And on the other side of that boundary, in the direction Voyager 2 was traveling when it sent its last coherent signal, the plasma environment has properties that correspond to a region of interstellar space that is denser, colder, and more magnetically organized than anything in the models of our immediate stellar neighborhood, a region that our instruments have never sampled before, a region that our models did not predict in the form that Voyager 2 appears to have encountered it, and a region that Voyager 2, losing power at a rate that will render its scientific instruments permanently offline within the next few years, may have had time to touch the very edge of before its ability to send back data disappears forever. The timing of the transmission compounds the scientific significance in a way that is difficult to overstate. Voyager 2's power supply has been declining for decades as the radioactive plutonium in its thermoelectric generators slowly decays. Mission controllers have responded by progressively shutting down instruments and heaters to conserve the remaining power for the highest priority systems. The plasma wave subsystem has been one of the last instruments kept operational, specifically because the interstellar medium measurements it provides are irreplaceable. No other instrument anywhere in the solar system is in a position to make in situ measurements of the interstellar medium at Voyager 2's location and distance. When Voyager 2 finally goes silent, that measurement capability is gone permanently. There is no replacement mission currently approved or funded that will reach comparable distances within our lifetimes. The data in the final transmission may be the only direct measurement humanity ever obtains of the boundary region of the local interstellar cloud and whatever lies beyond beyond it. Every number in that transmission, every plasma density reading, every magnetic field vector, every wave frequency detected by instruments designed in the 1970s and now operating at the absolute limit of their power budget 47 years after launch, is potentially irreplaceable scientific data about a region of space our species